In the first part of this lecture, we discussed the concept of force, and we have shown that when you have two charges, they do affect each other with a force, and the force that each one of these charges is affecting the other one with, it's along the line moving from the first charge to the affected charge. And there are two forces. They are opposite to each other. The force affecting the first charge is opposite the force affecting the second one. So every one of these two charges affect the other one with a force. Now, the concept of electric field is actually derived from the concept of force. And here in this figure, if you take a look at this one, we have a charge Q. And this charge Q here, is located at the position R1 from the origin. And here we put a test charge, a tiny test charge Q at this point. And of course, because of the presence of the big charge Q, it will start to try to affect it with a force along the vector R12 shown here in this direction. Now, the definition of the electric field is the force per charge. So you try to get the expression for the force at this point and then divide it by the value of this charge. And the reason why we make the value of the charge goes to 0 is that we would like it not to perturb any distribution that may exist of charges. Remember, if this is a big charge, it's going to affect other charges and move them from their places. But if it's a tiny charge, it's going to be affected by them, but it will have very little effect on the other charge. So we bring a very tiny charge, and then we calculate the field, and then the force, and then we divide it by the value of that charge. Another way of writing the expression for the electric field is simply to assume that the value of the charge is one column in the expression for the force. This will give you exactly the same answer. So the electric field, when I say there is an electric field of 5 volt per meter at a point, this simply means that if I put a positive charge at this point, it will be affected by a force. And the value of this force relative to the charge, so the value of the force to the charge is equal to this 5 volt per meter, whatever the value may be. So the force and the electric field, they have a really equivalent meaning. So basing on the expressions we derived from Coulomb's law, we know from Coulomb's law that the force between two charges, we derived that before. F is equal to Q1 Q2 over 4 pi epsilon R12 squared, and this in direction 1 2. So this is a force affecting the second charge due to the presence of the first charge. Now, if I put Q2 if I divide this expression by Q2, I obtain the value of the electric field at the point of Q2. So I will call this one here E, which is going to be equal to Q1 over 4 pi epsilon R squared, and this is A12. Okay. So this is what we have. So it is really the expression for the electric field is the same expression that we have for the force, but after we divide by the second charge, we make the second charge equal to 1 or divide by its value. So here the expression for the electric field resulting from a charge at the origin is this one here, and you could see that the electric field, if this is the origin, electric field is pointing in the radial direction from this charge. Okay, which means that if I put a positive charge at this point here, the charge at the origin is trying to push it away from it. Okay, this is what this means. The value of the force or the electric field is inversely proportional to the distance squared, which is the radius. So the radius from the origin, from the position of the charge to the observation point where I'm measuring the field, is what we call R here. Now, it's very important to remember two things. There is a position here of the charge, so the position of the source, and we usually give it we use the notation R dash. So R dash indicates the location of the source. So here R dash is equal to 0 here because it's at the origin, and the R is the point as which we are measuring the field. We call it the field point or the observation point. So for example, if I measure the field at this point, the field will be in the outward direction here. Okay, and it will have a value, certain value, depending on the distance along from the origin here as shown. So there is a source point and there is an observation point. This concept is very important, as you will see later. Now let's take a look at a simple example to illustrate the concept of electric field. We have a 25 microcoulomb charge is located at the point 3, 4, and 0 meters. We want to evaluate the resulting field at the origin in spherical and Cartesian coordinates. So here notice that the charge is not at the origin. The charge is at 3, 4, and 0, and we want to calculate the field at the origin in both spherical and Cartesian coordinates. So in this case, the r dash point is this point. This is a point where the source is 3, 4, and 0, while r is the origin. So now let's take a look how can we do this example in both spherical and Cartesian coordinates. So as I mentioned earlier, it's helpful to usually to draw a diagram. So here we draw this diagram. This is the origin here. This is the point 0, 0, and 0. This is where my charge is. At this point here, I think it's 3, 4, and 0. Okay, so we have this point, and of course we want to we evaluate the field here. So this is my observation point, or this is my field point, because if there is a positive charge here, it will try to repel any positive charge that can exist here. If I put a test charge here, this charge Q, capital Q, will try to push it in the outward direction. This direction here is minus r, direction of minus r. So in spherical coordinates, this direction is the direction of minus r. So as you could see here, the vector pointing from the point of the charge Q1 to the origin, I call this vector here R10. So R10 is really this vector here. This one should have 1, 0 to it. This is a vector pointing in this direction. Okay, this is R10. R10 is equal to its modulus. This is a modulus multiplied by minus r. Remember, the field here is in the minus r direction, in the direction pointing from the source to the position of the test charge, which should be here. So this length from here to here, we can find it through the length from the components. So it's equal to square root 3 squared plus 4 squared. This is equal to minus 4 in the AR direction. The expression for the electric field is, as I said earlier, is the same as the expression for the force, but we have only one charge, because the other charge has been already replaced by one Coulomb, or we divided by it. So the expression for the electric field here in this case is Q over 4 pi epsilon modulus R10 squared in the minus AR direction. This is a force affecting any charge in the origin divided by the value of that charge. So we substitute here with the values that we have. The charge, the result which will create the field, is 25 microcoulomb. So here micro is 10 to the minus 6. We divide by 4 by epsilon, and as I said, if I don't give you the value of epsilon, you'll assume it is that of vacuum or of air. We agreed that air has a refractive index very close to 1. And then the last thing, you divide by r squared. R squared is the distance from my source point where the charge Q is to the origin, which is 5. So this is 5 squared in the minus AR. If you simplify all this, 5 squared will cancel with 5 squared. 4 pi will cancel with 36 pi to end up with 9. So you end up with minus 9 AR. 10 to the minus 9 will cancel with 10 to the minus 3, will give you 10 to the power 3. Then your electric field is minus 9 AR, and the units for electric field is volt per meter. So here the unit that you're going to be getting is kilovolt per meter. This is the value of the electric field here in this case. Of course, if you want to do this example in Cartesian coordinates, we can exactly do the same. We have a point which is at a certain point in space. It's a point here 3, 4, and 0 here. Okay, and we want to calculate the field at the origin. So the vector, we have to calculate the vector pointing from point 1 to point, I didn't really call it 2 here, I called it 0. So I call this one point 0. So I'd like to calculate the vector R10 in Cartesian coordinates. And as we learned from the vector analysis part, R10 is equal to R0 minus R1. So this here is the origin. It is all zeros. So this is minus 3ax, 4ay, and 0. So this will give you minus 3ay minus 3ax minus 4ay as shown here. So the unit vector pointing in this direction. So I need a unit vector here for the expression for the electric field. You divide this vector which you got by its length, and its length is 5. So you divide this one by 5, and this is the expression that you will have. Then the electric field can be obtained by simply using the expression for the electric field. You make a substitution. It's exactly very similar to what we did earlier. This is a charge that we have, 25 micro Coulomb, divided by 4 pi epsilon, and as I said, epsilon is that of vacuum unless otherwise mentioned, divided by r squared, the distance between the charge and the observation point, 5 squared. This is a unit vector pointing from my charge to the observation point, and this is really the minus AR. This is a minus AR, but it's written in Cartesian coordinates. So this all will simplify to give you this the same answer that we got earlier. This is 9 and this is minus AR. So the answer here is this number, minus 27 over 5 AX minus 36 over 5 AY kilovolt per meter. And of course this kilovolt came from cancelling 10 to the minus 9 with 10 to the minus 6. So this is the answer that you have at this point. We discussed earlier how to get the electric field resulting from one charge, but in reality we never have a situation like that. We have a certain distribution of charges, and we'll start by first discussing the simplest case when you have a number of discrete point charges, and in this case we say that the field at one point is the vector sum of the fields resulting from each individual charge. And actually we use this concept all the time. If you have an electric circuit, it has all type of resistors and so on, inductors and so on. If you have a source here, it has certain polarity. You say that the response to this source, you can find it if you add another source. What we usually say, well, you apply superposition, you assume the first source does not exist, find the currents due to the first source, and then you assume the second one does not exist, find the current due to the second source, and then you sum them. And the reason you do that is that these are linear circuits controlled by linear equations. The same thing happens here. Because we assume that we have a linear medium, then the concept of superposition applies. The electric field resulting from a number of charges is a vector sum. So you find the field at any point in space, find the electric field resulting from every charge, and then do a vector sum to get the total field. What does the total field means? It represents the total force that will affect the total charge, the total force affecting what we call a test charge at this point per charge after we divide by the charge. So this will give you what is meant by the field. Electric field is really another way of representing a force. So just to remind you first a few things we have to remember. The electric field resulting from one charge at the origin is equal to Q over 4 pi epsilon r squared dr. This is at any point at a distance r from that point, okay? So this is fine. This is when your charge is at the origin. So in this case, if you recall, I mentioned this earlier, this is your charge here in the origin, and it's trying to push all positive test charges away from it along the radial direction, and the strength decays as 1 over r squared, and this is why we get this expression here, which we have seen earlier. Now, if the charge is located at an arbitrary point r dash as shown here, and it is really a notation widely used in electromagnetics to call the location of the source r dash. So this is where my charge is. It has a position vector r dash relative to the origin. It has 3 coordinates x dash, y dash, and z dash. And this is where the point I would like to measure the field. It has a position vector r. So what we have to do, we have to find the vector pointing from here to here. This is the vector, I will call it here, this is the vector pointing from here, I call it 1, 2, r1, 2, which is really equal to r minus r dash. You subtract this one minus this one, okay? And this will be pointing in the unit vector, pointing in the outward direction, so this unit vector here. And of course, there's another expression for that. If we replace this AR by the vector itself, by the vector r minus r dash, which is really this one here, the vector pointing this direction, and divide by its length, you get the length cubed in the numerator. So this is the field resulting from a single point. What if we have more than one point charge? What if we have more than one point charge? In this case, superposition do apply, and you sum them all at the point where the field is being measured. are being calculated. So here I show you an example, and before I go to the formula and the top, I just show you an example for where you have two charges. So there is one charge here, it has a value of 2q, and there is another charge here, it has a value of minus q. And I would like to observe the field here at this point. This is my observation point, and these are two charge points. Okay, so because this is the positive charge, if I put a positive test charge here, it will try to push it in the outward direction, in this direction. So the electric field resulting from this positive charge will be in this direction, in the direction of E1. Now, because this is a negative charge, if I put a test charge here, a positive test charge here, it will try to attract it. It will try to pull it in its direction. Okay, then the field E2 is in this direction. So now at this point I have two fields, E1 and E2. And if I do a vector sum, if I complete the triangle, I'll get my resultant field is this one here, this value E, which is resulting at this point. So as you can see, what we did, we calculated the distance, we calculated the vector pointing from here to here, which is really r minus r1 dash. We calculated the vector pointing from here to here, which is r minus r2 dash, and then we substituted the expression for the vectors and then we summed them. So in general, for any charges, this is the expression that you should be using. For every point charge, calculate the distance between this point charge, it's at location Rn dash, and the point where you are measuring the field. An is a unit normal pointing from your charge, from the nth charge, to the observation point R. And Qn is really the value of the nth charge. You do all this summation, you do vectorial sum, and then we took here 1 over 4 pi epsilon as a common term. You do this vectorial sum, you end up with the total field here. So the total field at any point in space is simply the vector sum of the fields resulting from every individual charge. For the two charge example I've shown you earlier, you can write it of course in a Cartesian coordinates. This is exactly the same way I mentioned earlier. The field resulting from the charge Q1 is Q over 4 pi epsilon r. Here we divide it by the length to the power 3, and then we multiply by the vector itself. This is another form, as I explained. The Coulomb's law will have two forms. Either use a unit vector in the numerator and then divide by the length squared, or use the vector itself and then divide by the length cubed. And this is what we have here. This is the length cubed. Remember that the length is square root of the sum of the squares of the components. So this is the field resulting from the charge Q1, this is the field resulting from the charge Q2. These fields are calculated at the same point, x, y, and z. And the charges are a location x1, y1, and z1 for Q1, and the x2, y2, and z2 for Q2. If you calculate these two expressions and you get their vectorial sum, this will give you the total electric field at the point x, y, and z. Any point x, y, and z actually in space. To illustrate the concept of superposition, we'll consider here this example. We have two 10 nanocoulomb charges, and they are located at position 0, 0, and 4 meters, and 0, 0 at minus 4 meters. We would like to find the total electric field resulting from them at the point 0, 4, and 0. So as I said earlier, it's good that you start solving any problem by drawing a diagram to know where these charges are. This may give you a hint, to give you a better understanding of how you should proceed. You can see that this charge here is in the positive z direction at 4 meters from the origin. This one is in the negative z direction at minus 4 meters from the origin, while this one is on the y-axis at 4 meters from the origin. So we can draw a diagram to see how these charges work together. We have here this diagram. So this is a charge Q2, this is one charge here, the second charge here. This is where I want to measure the field, and as I said, this field is nothing but the force that would affect a test charge if it's put here per the value of that charge. So after I divide the value of that charge, this charge here, if I put a positive charge here, will try to push it in this direction, so it will create this field E1. This charge here, it will try to push the test charge in this direction, so that this charge is put here, so to in this direction, we get a field E2. Because these two charges are equal, we could see there is some degree of symmetry here. The field E1 can be decomposed into two parts. as we did before in different course, in different examples, it can be decomposed into a component in z direction and a component in the y direction. The same thing you can do it for the field E2. You can decompose it into a component in the z direction and a component in the y direction. As you could see, the two z components, this one here and this one here, they cancel out because the two charges are equal. The two charges have equal value. Then the z components will cancel out, while the y component will be double that of a single charge. So this problem, because of its symmetry, we can immediately tell, without doing any math, that this problem, the field at this point, will not have a z component. The two charges are trying to push the net result of these two charges is trying to push a positive charge along the y-axis, and the reason is this field here will have a component in the z-axis, positive z, while this field here will have a component in the negative z, and these two are equal and they cancel each other out, and they are left only with double the field resulting from a single charge in the y direction. Now let's see how the math is going to work. Of course, to calculate the field resulting from any one of these charges, calculate first the vector pointing from the charge to the observation point or the field point here. So you have to calculate this vector, and you don't have to get that length. So the length is a modulus of this vector, and then we use the expression for the electric field, Q over 4 pi epsilon divided by r squared AR. So here you start substituting into the expression. I'm trying here to get the field resulting from the first charge only, and I will show you why. Because I know from symmetry that the total field is double the y component of this field. So I'm trying to get Q over 4 pi epsilon. R13 is the vector pointing from the charge Q1 to the observation point, and the unit vector in this direction is A13. So here the charge has a value of 10 nano Coulomb, so it's 10 to the minus 9, divided by 4 pi divided by epsilon, 1 over 36 by 10 to the minus 9, divided by the length square, and the length is not that difficult. One of them is 4 in the positive z, the other one is 4 in the positive y, then the length is 4 square root 2, so this is the length squared. The unit vector pointing from the first charge to the second charge, again it should be clear where did I get this one from. If I draw a vector pointing from here to here, this is 4 here, this is 4 here, so this vector will give you 4ay minus 4az, and the length of that vector, of course, as shown here, is 4 square root 2. So this term here that you see here, this is a unit vector pointing from the location of the charge Q1 to the observation point on the y-axis. Now if I start to simplify the expressions, I will get here this answer for the electric field in the E1. So 10 to the minus 9 will cancel 10 to the minus 9. This one and this one will cancel to give you 9. 9 multiplied by 10, you get 90. Divide by this term, which is 32. So you get 90 over 32 multiplied by the unit vector in the pointing from the charge to the observation point. Now the final answer, and as I got from the figure, and you don't have to do that, you could have got E2 as well, and then you sum them vectorially, but I made here a shortcut. I said, okay, I know that this z component will be cancelled out with the one that we get from the other charge, so I will cancel this one out, and then I'm going to multiply the y component by 2. So my field will not be equal to 90 over 32. It's going to be 180 over 32, 1 over square root 2 a pi, 1 square root 2 ay. So this is what we have here. This is the total field, and if you simplify, you get an answer of 3.977 volt per meter in the y direction. And I do encourage you to calculate as well E2 and do vectorial sum of E1 and E2 and show that the z component will indeed cancel out and the y component will be multiplied by 2 as I did here. But I know as I was able to make use of the symmetry, this saved me a few steps in getting the answer, and this is something you will get used to in solving electric field problems.